Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face Trending List, published on February 26, 2026, just yesterday. It demonstrates that by letting a model diagnose its own weaknesses and generating targeted training data, an 8 billion parameter model can actually outperform the massive GPT-4o. The paper is titled, From Blind Spots to Gains, Diagnostic-Driven Iterative Training for Large Multimodal Models. And as we'll see later, the fact that they achieved this with only about 4,000 training samples has huge implications for efficient model training. And for those interested in the implementation, the authors have shared their code on GitHub. On Hugging Face, the 7 billion and 8 billion parameter models are available for download, including usage examples, so you can test these multimodal reasoning gains yourself. Figure 1 contrasts the traditional approach with this new framework. On the left, the visplay method relies on limited static vision content, which often creates unstable data because the images never change. In the middle panel, DPE fixes this by using agents equipped with tools like retrieval and editing to generate diverse visual content. Crucially, a diagnostic step, represented by the robot analyzing a bar chart, identifies weaknesses to create adaptive training data. The charts on the right show the impact. While the blue visplay line fluctuates on complex tasks like Sharksieve, the orange DPE line steadily climbs with each iteration. Well, Figure 2 details exactly how that loop works, step by step. On the far left, the process starts with the diagnosis phase, where a specialized agent analyzes the model's previous answers to pinpoint specific weaknesses, like trouble with geometric charts. In the large middle section, this diagnostic report feeds into a multi-agent team. A planner directs an image selector to find or create fresh visual data, such as this diagram of a roof, using tools like web search or image editing. Then, a question generator and validation agent ensure the new training examples are both relevant and solvable. Finally, on the right, the model trains on this high-quality data using Group Relative Policy Optimization, or GRPO, before the cycle repeats. So Figure 3 breaks down why the components we just saw, diagnosis and image tools, are actually necessary. On the left, looking at the CHAR14 benchmark, and on the right for Math Vision, the blue line tracks the full DPE method. It climbs steadily, showing the best performance. In contrast, the orange line shows what happens without the diagnostic module. Notice how it flatlines or fluctuates because the model isn't fixing its specific errors. Finally, the green line removes the image editing tools, and while it improves initially, it quickly plateaus, proving that visual diversity is essential to avoid hitting a ceiling. Alright. Table 2 puts those gains in perspective by comparing the DPE-trained 8 billion parameter model against some massive industry heavyweights. In the bottom row, the DPE model achieves an average score of 64.4. That beats the 72 billion parameter Qwen 2.5 model, which scores roughly 62, and even surpasses GPT-4o at 56.1. It is particularly strong in visual math, setting new state-of-the-art records on Math Vista and Math Vision. This confirms that smart diagnostic data generation allows smaller models to punch way above their weight class. While Table 2 just highlighted the final performance against giants like GPT-4, Table 1 breaks down the training stability compared to visplay, a standard self-evolving baseline. Looking at the Q.5 results on the left, notice how visplay fluctuates. On the LMMs benchmark, it actually drops to 49.3 in iteration 2 before recovering. In contrast, the DPE columns show a steady monotonic climb, reaching 56.44. This smooth improvement repeats across tasks like OCR, and the rightmost section confirms the method scales, boosting the Qwen 3 model to a final average of 68.04. So, Figure 4 visualizes how the model adjusts its training diet. The chart uses concentric rings to show the data distribution, starting with the base seed set in the center and moving outward through 3 iterations. Notice that the colored slices change size. For instance, the green text-intensive section expands in the first ring because the diagnostic agent detected a weakness there. Later, the focus shifts to areas like math formulas, ensuring the model continually practices what it finds most difficult. Wrapping up, 2 takeaways stand out. First, precision beats scale. By targeting blind spots, an 8 billion parameter model outperformed the massive GPT-4o, using only a few thousand samples. Second, the diagnostic loop ensures stable, continual learning where other methods stall. This implies a shift toward adaptive, self-correcting training pipelines. That's it for this episode of the AI Research Roundup. I'm Alex, thanks for listening.